On the screen are a family of curves for a 2N3906 transistor. There's nothing really unique about generating these kinds of curves. They're done routinely with devices called curve tracers. In the Y direction is the collector current, and in the X direction is the collector to emitter voltage. So each of these curves represents a particular base voltage, or base current actually, so that, for example, this one is a base current, this is a different value, and so on. So if there's nothing special about this, why am I showing it? Well, the reason is that what I'm actually doing is I am using the analog discovery to generate those curves. And once again, I'm not doing that to encourage people to try to produce commercial curve tracers with the analog discovery. Instead, what this video is going to be about is the features of the analog discovery that allow you to do really neat things like this. Now, I will point out that there is no additional hardware. Let me repeat that. This is done entirely with the analog discovery and the waveform software that comes with it. The only external device is the 3906 transistor that we're doing the traces on. At the end of the video, I'll talk a little bit about how you might want to, some changes and some additional hardware you might want to add to gain some additional advantages. But you can repeat this experiment with just an analog discovery and the waveform software. So let's talk a little more about that. But before we talk about the analog discovery, let's talk just a little bit about the traditional way of doing these curve tracers. I decided to do this experiment because I was thinking about the issue of the simple curve tracers. Now, you'll find this sort of circuit all over YouTube. Some people call it an octopus, some people call it a curve tracer. A variety of people have done videos on this. In fact, Alan, W2AEW, did a very nice curve tracer with a step generator for the base current and so on. Traditionally, what the octopus was created from was a little filament transformer, usually about a 6.3 volt filament transformer. I've shown two diodes here so that you can switch, but you don't even really need the diodes. The problem is that if you don't use the diodes, you may be stressing the transistor because you're applying a negative instead of the traditional. For example, in this case, if this were a 3906, you want a positive voltage on the collector relative to the emitter. But this will not only produce a positive voltage, but also a negative voltage in the absence of the diodes. So the diodes are sometimes put in so you can switch between NPN and PNP transistors. And then what this shows is a very simple connection with a variable resistor to apply base current to the device to turn it on. The problem with this approach is that this signal is varying, so that means that the base current varies quite a bit. If you brought a stabilized supply in to produce the base current, you can get fairly nice curves. And over on the right are the curves you would get. This is the collector voltage from 0 on this end to the maximum. And this is the collector current. Now, traditionally, the way you read the collector current is you insert a small resistor in the collector lead, and then you put the vertical channel of the oscilloscope across that resistor. The horizontal channel of the oscilloscope is reading the collector to emitter voltage, in other words, this voltage here. And the voltage across the resistor represents the collector current. And traditionally you get curves like this. Now understand, you don't get pretty curves like this on a lot of these kinds of testers because you have to find a way to produce a step base current. good curve tracers, and there are many that have been produced over the years. They're not so popular anymore because fewer people use discrete transistors. But nonetheless, this is the base current. In other words, this is a particular base current. This is a slightly higher base current, slightly higher, and so on. And you used to find curves like this all the time in transistor manuals and other things. They can be useful for designing transistor stages, but we're not going to go there in this video. Instead, what we're going to do is show how you can replace all of this logic or all of this hardware and more with the analog discovery. Here is the entire setup. On the breadboard, you see 2 resistors, a transistor, and the analog discovery connected by the fly wires that come with it. You don't even need the BNC adapter board for this. So except for the transistor, the only additional hardware you need are 2 resistors. We'll talk about those in a second. On the left is the circuit, so let's concentrate on that first. Here is how it's set up. The transistor has a resistor connected to its base and a resistor connected to its collector. Waveform 2 of the analog discovery is connected from this point to this point, and it's generating a triangle wave. Very simple to do that. It's one of the standard basic waves that's available in the analog discovery, and we'll look at that in a second. The only thing that's a little peculiar is you want to offset your triangle so that instead of going plus and minus from 0, it goes from 0 up. So, for example, if you set a 2 volt voltage for your waveform generator and then you offset it by 2 volts, that means you'll be going not from 0 to plus 2 and minus 2, but rather from 0 to 4. So this triangle will be going from 0 to 4 volts. That voltage is being applied across the transistor and the resistor in combination. Waveform 1 is being used to generate a stair-step, and that's not an available waveform, but they're very easy to create, and I'll show you how I did mine. Once again, there's a resistor in the base. These resistors are there simply, in this case, to limit the current flowing into the base, and in this case, to provide something to develop a voltage that is proportional to the collector current. Channel 1 of the oscilloscope is connected across the transistor, and channel 2 of the oscilloscope is connected across the resistor. Now, you might ask, well, first, why in the world do you even need a curve tracer? If you recall a circuit that I was using a few weeks ago to do some experiments, it used complementary output transistors. Now these are very low power transistors, but you can get very high power transistors that you can use in hi-fi amplifiers or other applications where you want to drive a fair amount of power. But to work effectively, what you need is a matched pair. In other words, you need, in this case, a 3906 and a 3904 that have very similar characteristics. And one way to do that is to use a curve tracer. But before we talk any more about the analog discovery, I want to do a very quick overview for those of you that might be interested in some of the history here. This is an article out of the January 1975 QST magazine called The Octopus. And you'll see at the top here is the circuit that he proposes. And this was originally developed by a technician in the U.S. Navy for troubleshooting electronic equipment on board ships in the Navy. But it proved so useful and so popular that it was later published in QST as the Octopus, and there are, I don't know how many designs of the Octopus out there, but there must be at least hundreds, if not thousands. In the May-June 2017 issue, not World War I, QEX magazine, 2017 May-June issue, is this article called Improved Performance of Your Octopus Curve Tracer Using a Single Voltage Transformer. You might want to go look for that. Now, unfortunately, QEX and QST are not available on the AmericanRadioHistory.com website, where I normally refer people for magazines. But if you are a member of the ARRL or know a member, you can get access to these through the ARRL website. So now let's take a look at how we did this on the analog discovery. This is the waveforms window, or waveform generator window of the Waveforms 2015 software that comes with the analog discovery. On the top is waveform generator 1 or channel 1, and on the bottom is channel 2. You notice that channel 2 is generating a triangle wave, and that is a fairly simple way, or there's a very simple way to do that. Triangle is one of the basic waveforms. You may notice that I have a 2-volt offset and a 2-volt amplitude. That means that my signal is going from 0 volts to 4 volts and back to 0 again. I'm using a triangle to sweep the collector. In other words, the collector voltage goes from 0 to 4 volts and back to 0 again. Now, one of the limitations of the analog discovery is it'll only produce 5-volt maximum signals. And we'll talk about how we might get around that toward the end of this video. But for right now, we're generating a 5-volt or a 4-volt triangle wave on waveform 2. Waveform 1 is a little different. Waveform 1 is a stepped, what's called a staircase. This is not hard to do, but it does require that you use the custom waveform and that you create the staircase. So let's look at how you go about doing that. I've zoomed in on waveform generator 1, and you'll notice up here that the type of wave is custom. Okay? It has simple, basic, custom, and then some others, play, sweep, and modulation. Normally it comes up in the simple mode, and the triangle wave is a simple wave. You can see that down below here. Triangle, simple. But for what we're going to do a custom. Then we're going to click on Edit, and a new window comes up that looks like this. Notice that I have the you can generate a custom from a function, from a math equation, or from values. I'm using values. Notice over here that I have values of 0, 1, 2, 3, and 4. I've also turned on normalize, which you can see down here. And then you click generate. And what it does is it generates this waveform that you see over here. Starts out 0, and then up and up and up and so on. Let's go back and look at how we have this set up. We have a frequency of 1 hertz. Now, what that means is that the generated waveform will go through its full staircase once per second. So it takes 2/10 of a second, 4/10, 6/10, and then 8/10, and finally at the end of 1 second it goes back to 0 again. So that's how I generated the staircase. Now, once again, notice I have the amplitude set to 2 volts and the offset set to 2 volts. What that does is it causes the waveform to start at 0 volts. And you see that 0 volts is here, 1 volt, 2 volts, 3 volts, 4 volts. You notice that 2 volts, which is the offset value, is in dotted lines. And so we're going from 0 volts to 4 volts with our stair step. So this is the pattern we're applying to the base. This is the pattern that we're applying to the collector on the bottom. And there's just one more thing that we need to talk about, and that is you want this triangle to reach its peak in the middle of this stair step and then go back to 0 just as this step starts. That way you have synchronized these two waveforms. So how do you do that? Well, the first thing you have to do is you have to turn on synchronized up here. Notice I say it's synchronized. Then I synchronize it by setting the phase of the triangle to 270 degrees. 270 degrees is basically minus 90 degrees. The reason is the waveform generator normally starts at 0, but remember we're starting it from its most negative value. So we have to shift 1/4 cycle to the left, or minus 90 degrees. Well, 270 degrees is the same as minus 90 degrees. So I have set a 2-volt amplitude, a 2-volt offset, and a 270 degree phase difference. Now I will also point out one thing that happens when you use synchronizing channels. Remember that when you're running synchronized channels, you're essentially running one 2-channel generator. And that means that you'll notice that the run here is grayed out for channel 1 and channel 2, and instead you can only run all. If we weren't synchronized, then you see you can run individually. But because we have synchronized the two generators, we can only run all at once. Okay, now let's take a look at how we might improve this setup. Before we talk about improving it, we need to talk about some of the limitations. Because the waveform generators of the analog discovery will only generate relatively small amounts of current, in the milliamperes of current, you have to use a fairly large resistor here, and you can't drive a lot of base current here. However, if you were to insert a current amplifier on the output of waveform generator 2 and use that amplified current to supply the current here, you could lower this resistor to a very low value. The advantage of that is that means that the driving voltage here and the collector voltage here are going to be roughly the same because most of the voltage will be dropped across the transistor. In the current setup, this resistor is fairly large to limit the load on waveform 2 generator. But if you put a simple 1-transistor amplifier in here, you can drive a lot more current. And that would improve the setup because you could then use a lot smaller sense resistor. Second thing is you could do the same thing for waveform 1. That is, if you were doing a power transistor here and you could generate enough power through an amplifier out of waveform 2 through an amplifier to supply the appropriate collector current, perhaps an ampere or 2. Then you need a base current that will cause that transistor to switch that or to drive that amount of current. So you need to amplify the output of waveform 1 as well. Now when I say amplify, I mean amplify the current. So you want a current amplifier. For example, a good design might be an emitter follower. Perhaps if you need more gain, you might use a Darlington emitter follower. The one other thing that I will mention about the analog discovery is, because it has differential inputs, unlike most of the octopus circuits that you see where this point has to be grounded, and then you have to invert one of the channels in your oscilloscope. In the analog discovery, you can swap the plus and minus leads of the channel 2 and channel 1 scopes. They do not have to be referenced to a common ground. So this is one of the advantages of the way the analog discovery is designed. And it facilitates this kind of thing. In fact, if you were to put in an NPN transistor instead of a PNP, you would want to change the offset of waveform 2 and of waveform 1 so that you would be driving from 0 to negative values on both of them. And you would want to swap the channels of the oscilloscope around. In other words, the positive terminal of channel 1 and the negative terminal would be swapped. Same with channel 2. And now you have an NPN transistor tester. The reason that might be useful is if you were trying to match, say, a 3904, which is an NPN transistor, with a 3906, which is a PNP transistor, you would want to be able to do a trace for each. So, using this kind of setup, you can create a little curve tracer. If you wanted to make this into a commercially, or I should say a more commercial grade circuit, what you would want to do is, as I pointed out, amplify the current of waveform 2 and of waveform 1, and you might want to provide switching so that you can switch channel 1 polarity and channel 2 polarity. If you do that, you might also want to swap the polarity of waveform 2 and waveform 1. However, I point out that unlike the scopes, the waveform polarity is referenced to ground. So it's better to use the offsets inside the analog discovery software to change the polarity of these waveforms. But on the scopes, you could put a double pull, double throw switch here so that in one position it was configured for NPN transistors and in the other position for PNP transistors. Then you could go through your set of NPN transistors looking for the one that most closely matches the PNP of the same complementary pair. I hope that this has been interesting to most of you. What I'm trying to show is that just with the analog discovery, you can generate a sequence of very interesting circuits and applications. There's a lot of power in the analog discovery. And lest some of you think that I'm pushing the analog discovery for reasons other than just because I like it, as I've pointed out before, I don't have any connection to Digilant except as just a user, and nor do they pay me anything, nor do I get anything. You may notice that I don't even put advertising on my videos. So the purpose of these videos is to try to generate not only use of instruments like the analog discovery, but discussion, innovation, and improvements to extend the analog discovery or similar instruments to new applications. In other words, broaden the horizons of the community. I hope it has spurred a little interest in you. I hope you've been interested in this video and will look forward to some future videos. But in the meantime, have a nice day.